Okay, the Black-Scholes equation, it looks complex. Yes, but you can make it more simpler using another variables. You can make a variable change in order the Black-Scholes equation to look it simpler. And here, just for curiosity, will make will indicate the variable change that you need to make, which is this one here. This is it's not important, but just we're doing that just for curiosity, so that using that variable change, so going from v to this new u, which depends on the variable x and tau, which are connected in this way. The x1 is connected in this way with the asset price with s, and tau and t are connected both in this way. So using that change of variables, you can transform this complex Black-Scholes equation. Of course, the simplest case, the basic Black-Scholes equation, where sigma and r are constants, you can transform it in this new equation. So using that variables, the complex Black-Scholes equation, it will look much nicer, much simpler, which is in this way. And you know which is this equation. That's the diffusion equation. So even though this is just for curiosity, you can transform in some way using different variables the complex Black-Scholes equation to the diffusion equation. Of course, it's reasonable because we said before that the Black-Scholes equation is a parabolic equation. And the prototypical example of the parabolic equation is the diffusion equation. So it's a huge connection between the Black-Scholes equation and the diffusion equation. But it also has an important consequence. The diffusion equation has been deeply analyzed analytically. So it basically means the main implication from that is that the simplest Black-Scholes equation, that the one where sigma and r are constant, do also have an analytic solution. And I think it's important to mention what's the expression here for the general analytic solution of the Black-Scholes equation for different European options, which is this one, the one we have here. This is the general solution for the Black-Scholes equation for different European options. For example, here, this is the prefactor here, which depends on R, the maturity time, the time. Here we have the volatility. Here we have an integration from 0 to infinity. Here we have the exponential of all of this here. S is this variable here. S prime is the integration variable here. Here we have the payoff, so that specifies which kind of option we are evaluating here. We have to plug in here the payoff, which depends on S prime, and make the integration on S prime in order to have the value of the option corresponding to the one that has the payoff you're including here. And solving that integration here, you are evaluating analytically the value of the option. Of course, that's very interesting. Even though it's only valid for those simple cases where sigma and r are constant, but the option of having, the possibility of having an analytical solution, it makes the evaluation of this basic option much more simple. So of course, whenever the sigma and r that has some dependence, or whenever you're including other kind of features on the Black-Scholes equation, that the analytic solution becomes extremely complex, it's not possible to make, and you need to go to the numerical analysis. But for this simple case, there is an expression for analytic expression for the Black-Scholes equation. And of course, for example, you can just apply that to evaluate and calculate the value of the option for the simplest cases, which are basically the European call option on one hand, on the other hand, the put European option, which are these ones here. That's the solutions of the previously mentioned equation for these two cases here, where these ones are expressed in terms of this n function, where n function here is the one I'm writing here, which is, okay, is the one I'm writing here, which is the cumulative distribution function for normal distribution. And these D1 and D2 are these parameters you have here, which can be written in terms of the strike price, maturity time, volatility, different parameters, the interest rate, and the value of the asset. So again, here basically, just for curiosity here, we are including the connection between the Black-Scholes equation, the diffusion equation, and we have seen that in these cases, we can solve them analytically.